Hello everyone, my name is Sebastiano Gottardo, and I'm here to present MITHYS, which stands for Mind the Hand You Shake, and deals with protecting mobile devices from SSL usage vulnerabilities. So first of all, we're going to see a brief introduction about the context. We're going to talk about mobile applications, and we're going to talk about their security. Then we're going to focus a bit more on the SSL protocol and what it is, how it is used for, and what are its usage problems. Then we're going to talk about the Android situation, about the SSL usage problems, which is actually the problem that we want to solve with this work. And we're going to present MITHYS, which is our solution to this problem, and we're going to present also MITHYS app, which is our implementation of the MITHYS architecture. And finally, we're going to draw some conclusions. So in the last 4 to 5 years, the number of smartphones available worldwide has seen a huge growth. We're talking about 500 million devices in 2011, and some analysts have estimated that this number is going to grow up to 1 billion devices in 2015. But web service providers started paying a lot of attention to this phenomenon. In particular, they wanted their users to be able to use their service while they were on the move. That means on their smartphones. So together with the smartphone growth, also mobile applications started popping up as well, together with another solution. So first of all, mobile web service providers wanted their users to be able to use the service by giving them a mobile-tailored version of the website. But this approach came with a lot of disadvantages. For example, there were performance issues. Usually the mobile website had a subset of the original features of the desktop website. And also the lack of optimization made the experience completely awful. And native applications usually do not suffer from these issues, so it was the way to go. And together with the smartphone growth, also the number of mobile applications grew as well. And nowadays, Android together with iOS are the leading mobile operating system worldwide, with more than 1 billion applications in their stores per each. But these applications are used by everyday users, by us as well, to check our emails, to check our bank accounts, to make payments, or just to text with friends. And this means that these applications are handling our sensitive data and our private login credentials. And this also means that these applications have to be secure. And how is this security granted in a mobile environment? So there has been a lot of studies about the mobile security, in particular on Android. We see here some works about this. We have Tandroid, which is a system of monitoring the privacy of the user in real time by the information flow tracking. Then we have CREP, which is a system that enforces context-related privacy on smartphones. Then we have a more general study about the Android security topic about applications. And finally, we have MITHYS, which introduces operation modes on smartphones. But we're going to focus on Android, but these assumptions stay true also for other mobile operating systems, maybe under different names, or these features work in a similar fashion. So the first security feature that is offered by Android is called sandboxing. It means that each application runs in its own separate environment, which is mapped at the kernel level with its own process ID. And this means that an application can interfere with other applications in order not to hinder their working mechanisms. But while this is a strong security feature, it also limits a lot the flexibility of the operating system, and it doesn't allow an application to interoperate with other applications, which is something that we would like to be able to do. So Android also offers the permission system. So every time a user wants to install an application on his Android device, the system provides the user with a list of the permissions that the application is asking for. And the user can either grant those permissions, allowing then the applications to be installed and use, for example, if we take Skype, we allow Skype upon installation to access our phone book, which is correct. But the user might also deny these permissions, so it doesn't want the application in question to get access to that particular feature on the device, and so the installation is aborted. And finally, since almost every application is communicating through the internet to talk with a remote server, Android offers encryption and authentication over internet connections and HTTP and HTTPS requests. Thank you. So the most typical way of granting this security is by using the SSL protocol together with its successor, the TLS protocols. These two are two cryptographic protocols that are able to perform network data encryption and endpoint authentication over a TCP connection. We're not going to go through all the SSL handshake, the SSL protocol, but we're going to just focus on its first phase, which is called the SSL handshake phase. So whenever a client wants to establish a secure connection with the server, it just sends a first message, say, hey, I want to establish a secure connection. And the server replies with some cryptographic parameters along with the server certificate. For now, let's just assume that the server certificate works just like an ID document for the server. So it contains the name, the signature, the expiration date. And the client, upon receiving this server certificate, has to verify the server's identity with it. If this verification goes well, then the client and the server keeps exchanging security messages and cryptographic material in order to agree upon a common session key, which will in turn be used to encrypt the connection, and then they can start to communicate securely. But we said that the client must be able to authenticate the server. This is typically done by using the X.509 type of certificates, and by verifying the chain of trust for that particular certificate. It all works like this. So the server certificate is usually signed by a certification authority, which in turn is signed by a higher level certification authority, and up we go until we reach the top level certification authorities, which are called the root CAs. And what happens is that the root CA's certificate are typically bundled inside the mobile device or the web browser. So what the client has to do is take the server certificate and follow the chain of certificates up to the last one, which should be a certificate from a root CA that it knows. If this verification goes well, so if the chain of trust can be proved, it means that the communication is secure and the server who is saying it is actually. Otherwise, the communication must not be trusted and must be therefore terminated instantly. SSL is the standard de facto for secure communications over the internet, and is widely used. But this means that it should also be safe from from man-in-the-middle attacks. A man-in-the-middle attack works basically like this. We have a client which wants to communicate with the server, but a third entity, let's call it a bad guy, an attacker, puts himself in the middle and is able to intercept all the ingoing and outgoing communications from and to the client. But we said that the client must verify the server's identity, so it should be able to tell the web server from the bad guy. So it's all good, and we have nothing to worry about. But that's not the case, because two recent works from the CCS conference of 2012 pointed out that many SSL implementations are completely broken in a variety of environments. So the caveat from these two works is that the SSL protocol is secure per se, its design is good, it should work as expected, but if it's implemented in a wrong fashion, it might lead to unsecure connections, and therefore it might leak data that it shouldn't be leaking. And the most typical way of using the SSL protocol is by using a middleware. Back one, thank you very much. Is by using a middleware. A middleware is just a library that wraps lower level APIs and offers higher level APIs. But this means that, for example, let's take the OpenSSL library, the OpenSSL middleware. If for some reason the OpenSSL middleware is broken, it means that everything that stacks upon it and up to the applications are broken as well. And the authors of the first paper have categorized these misuses by type. So let's see a few examples. Let's take this few lines of code from the libcurl library, which is a wrapper library for PHP. We don't know what this whole thing means. We just see that the SSL verify peer option and the SSL verify host option are set to true, which is something that we would like to to be enabled. But what happens is that in PHP, the value true is automatically translated to 1, and the default value for these options to be enabled is actually 2. So 1 means do not do anything. So just keep the whole hostname verification and do not check for the certificate at all. And we have a similar situation in Java where these two variables in Java 6 and in Java 7 may be null by design, so it's something that it is supposed to happen. But since there is no else branch in this if statement, the old hostname checker part isn't done here as well. So no hostname verification again is done in this code. And this does not limit to PHP and to Java. We have several other environments where we have faulty SSL implementations, for example, and an NS-Stream library in Objective-C, the Apache HTTP client implementation, and a lot of PHP stuff, which is also used by PayPal. So everything is pretty dangerous here. And on Android, we have typically 3 ways of performing a network request, a secure network request. By using the 2 Java standards packages, by using the Android classes, which are maintained by Google, and by using the Apache HTTP client implementation. But the problem on Android is that it is Java-based, so in Java everything can be extended and its behavior can be modified. So on Android we have this particular situation where applications might check for a certificate in terms of expiration date and in terms of signature, but they are not checking the host name at all. So it means that I am the Facebook application and I'm receiving a certificate that comes from PayPal, but since it's valid in terms of signature and expiration date, I'm accepting it, even if it's not mine. And even worse, some other applications are accepting certificates that are self-signed. So it means that the whole certification authority part is skipped and it's not checked at all. Then we have another kind of attack, which is called the SSL stripping to certificates, but it's still a dangerous one because it consists in removing the S from the HTTPS request, turning into an HTTP one, and neither the client or the server complains about this lack of the S. And how do we exploit these weaknesses? Well, by performing a simple SSL man-in-the-middle attack. The scenario is similar. We have Alice, which wants to communicate with Bob, but Mallory, the bad guy, puts himself in the middle and is able to intercept all the ingoing and outgoing communications from Alice to Bob. And however unlikely you might think of this scenario to happen, you just need to think a bit about all the hotspots that we have in the country, all the Starbucks and McDonald's and coffee bars which are offering free Wi-Fi. And in this situation, you just have to set up a rogue access point. For example, if the Starbucks one is called free Starbucks, you just have to call it free Wi-Fi Starbucks. And the user is going to be tricked into connecting into yours, and you will be able to steal their data easily. So to demonstrate the problem, I'm going to show you a brief demo about this issue. Let's hope it all works. So I have a mobile device here, which is connected to my hotspot and to my computer, and I'm trying to log into the PayPal application with a fake password, of course. So let's open the PayPal application. Let's put my email address. Just a second. Okay. I'm about to try and log in on PayPal with a fake password, of course, and we should be able to see a request that fails, of course, because the password is wrong. But let's get into it. Let me zoom a bit. Okay. So as you can see, this is the request that has been performed by the PayPal application. It's a POST request to api.paypal.com. And we see my email address right here in plain text. And we are seeing that the password is being transmitted, and this is actually the password. Plain text, again, SSL is secure, is the password, is the fake password that I typed in. And as you can see, it's pretty straightforward to exploit these weaknesses. So let's go on with the presentation. And the Android situation turns out to be quite dangerous because, as you can see from the sad Android in the center, a lot of applications like Facebook, PayPal, bank applications, Dropbox, eBay, and stuff like that, it's very dangerous. And the authors of the second paper shared some interesting numbers. Out of 13,000 applications analyzed in a statistical fashion from Google's Play Store, they found out that nearly 1,000 of them were accepting all the certificates and all the host names without any check at all. They moved forward and they took 100 applications from the top categories on the Play Store, and they found out that nearly half of them were vulnerable to this particular attack that I've just shown. And even worse, the install base of these applications goes from 40 million users to 200 million users. So we're talking about 200 million users whose data is endangered. We've done our tests as well, and here you can see a list of the applications we manually tested. And PayPal, Facebook, Dropbox, LinkedIn, these are all leaking the credentials. And Volksbank, which is the application, unfortunately, of my bank, is vulnerable as well, so it leaked my credentials. We focus on solving this problem, but not just for currently vulnerable applications, but also to future applications which we don't know if they're going to be vulnerable or not. Hence, we present MITHYS, which stands again for Mind Handshake, and it's a clear word game with the SSL handshake phase. It is defined as a system architecture. It means that it's platform independent, and which is able to detect vulnerable applications and protect them from actual man-in-the-middle attacks. Even more, it works at the application level, so there is no need for you to run any custom ROM or jailbreak your device or ask for super user permissions. The structure of the system is here for you to see. We have two main components, which are MITHYS Proxy and MITHYS Web Server. MITHYS Proxy has two modules, which are called the Security Pentester and the Security Enforcer. So let's go through these two modules and see what they do. The Security Pentester module is the one which is able to detect vulnerable applications, and it does that by performing a friendly man-in-the-middle attack to the application. So every time an application issues an HTTPS request, it gets intercepted by the Security Pentester module, and a fake SSL certificate is forged by this module. It looks like the original one as much as possible, and is then given back to the application. If the application accepts this certificate, it means that it's vulnerable, because the application didn't do the right checks over the certificate. If, on the other hand, the application rejects it, it means that it's safe from this kind of attack, and we call it pen-proof. So in order not to hinder the normal operations of a pen-proof application, we whitelisted so it doesn't get tested. It doesn't get tested anymore. And the Security Enforcer module is the one who is able to protect vulnerable applications or not from actual man-in-the-middle attacks. And it works basically like this. Every time an application X issues an HTTPS request, it gets intercepted by the Security Enforcer module, which then splits the request into two. And the first one goes straight to the target web server, but the second one goes first to the MITHYS web server, which in turn issues the request to the target web server. The two certificates are then retrieved and given back to the Security Enforcer, who then compares these two certificates. If any mismatch is found, it means that something sketchy is going on and the communication cannot be trusted and it should be terminated immediately. So this is the complete workflow of the MITHYS working mechanism. For example, let's take PayPal. PayPal issues an HTTPS request. We check if it's whitelisted. If it's whitelisted, we execute the request as is with no further interception or anything else. But if it's not whitelisted, we check if it is secure via the Security Pentester module. If it's not secure, then the Security Enforcer is activated and protects the whole application. And if the application is secure, if PayPal is secured, we whitelist it, and then we just execute the request as is. But we didn't just design this architecture. We wanted to see its feasibility and how it behaves in in a real-world environment. So we went on and implemented this, the MITHYS architecture by means of MITHYS app, which is a fully working Android prototype. Here you can see some screenshots. We have a blacklist, which lists all the vulnerable applications, and we have a whitelist, which is much shorter and lists all the PAN-proof applications. And every time a new PAN-proof application is found, we show the user this nice dialogue where we say, hey, Twitter is secure. You can use it without any further ado. And let's move on. Thank you very much. And we wanted to assess how good our implementation was, and hence the MITHYS architecture. So we've done some tests, and first of all, we wanted to see how the security pen tester is good at detecting vulnerable applications. And we can say that we had 100% match with the results from the authors of the second paper. And the most worrying data about this is that just 2 out of 20 applications are found to be PAN-proof. And the security enforcer module is a bit trickier to assess because since it splits the request into 2 separate requests, it means there is an additional delay. And we tried to measure this delay, and we found out that we have a 30 to 50% additional delay, which translates into 5 seconds on average. But we have to stress that we took the worst case here because we wanted to see the most network-intensive operations, which are the login and the logout. And also, however, MITHYS app is a fully working prototype. It has not been optimized yet. So by introducing, for example, certificates cache, or by grouping the network requests, the performance can be improved a lot, and this delay can be reduced for sure. Okay, to wrap up, SSL is a widely used protocol, but not always understood by developers who, due to misleading APIs or confusing the documentation, or just because they don't want to bother with security topics, it's really not fully understood by them. And this means that faulty SSL implementations are everywhere and are endangering the user's data. But thanks to MITHYS, we offer a solution to this problem. And moreover, it's platform independent, so it's not limited to Android, but it may work also on iOS and Windows Mobile and whatever you want. And finally, it's not just a design. It has been implemented, and it actually works by means of the MITHYS app prototype that we implemented for Android. So I'm done. So thank you very much. If you have any questions, I'm here.
Is the app on the market yet?
Nope. Okay, I've been asking if the application is on the market yet. The answer is no. I bet you want to know why. Yeah, you want to know why. Well, the thing is that it's a prototype. So since the user is picky and wants to install anything on his device which is not fancy and it doesn't explain very well what it's doing, I figured that it didn't do any good to just publish it. I would rather wait for someone to pick it up and clean it up and like make it that it works always for every user with the least possible interaction for a user to configure it. So that's basically why.
I do have a question. Did you try to test those apps, those 20 apps later on, so later this year, for example?
Yeah. So I've been asking if I've tested these applications during the year again. And the thing is that while we were working on MITHYS, we were also in contact with these companies like Dropbox, like Google. I tried to contact as much as I could. And many of them just ignored this issue. But for example, with Dropbox, they took care of it. Like they didn't think it was that big deal, but they took care of it, and the application was then safe from this kind of attack.
Okay, cool. Thanks.
In your application, do you have friendly man-in-the-middle attack? So, which permission your application require, and how can a malicious application producer could exploit your method to do a man in the middle inside the device?
Okay, it's quite hard to repeat the whole question. I've been asked what permissions the application is asking for, and if there is a way for another attacker to do what? To
produce a malicious application of yours.
Okay.
That exploit
okay.
attack inside the phone.
Okay, so there are no special permissions, just the network one, like access to network and just database writing permission. So that's basically it. The thing is that there is a manual procedure requested by the user, because the user has to manually type the proxy address on the Wi-Fi connection, on the Wi-Fi configuration connection, and there is no way at the moment to bypass this manual step. So first of all, for an attacker to exploit this kind of attack inside the mobile phone, it would have to set the proxy without the user noticing it, which is not possible on non-rooted Android devices. So this is the first obstacle that I can think of right now. Okay.
Someone keeps on asking me, for example, why we did implement this as external. I mean, one of the components is an external web server, right?
Yep.
So people are asking why you didn't implement everything in the phone, because basically you can just do a proper check of the certificate.
Yeah, but we needed a third party here. We figured that, let me just go back right here. So the thing is that if we did everything on the mobile device, we are ensured that somewhere here there is another man in the middle which is attacking us. And we wanted to be sure that there was no way for anyone to put himself here while we communicate from the mobile device to the web server. And this is the case. I mean, there is no way for anyone to put himself in the middle, because we are actually doing the right checks for the SSL certificate. So whatever certificate that doesn't match in a one-to-one comparison to the one of the MITHYS web server, which is bundled inside the MITHYS app application, whatever other certificate it's received, we see that it's not the original one, so we drop the communication right away. So there is no way that someone can attack this segment of the communication. And if, on the other hand, there is a man-in-the-middle attack going on here, so when we cannot see somewhere here, we can detect it, because we know that this part of the communication is secure, and we can retrieve the SSL certificate. So if that one is altered, we can notice on the security enforcer. Okay.
Other questions? Okay, if there are no other questions,